and title is Lorentz symmetry violation effects on quantum dynamics of scalar particles. So I request the speaker to talk on.
Hello, am I audible?
Yes, you are audible.
Just a minute, I am sharing my slide.
Dr. Ahmed,
Yes, sir.
please switch on your video.
Please allow me. I am joining through mobile. Hello.
Yes, sir.
Whether my presentation is visible?
Yes, everything is fine. Please go ahead. In the slide mode.
Okay, thank you very much.
Please,
Everyone.
slideshow from the beginning.
My talk is basically quantum dynamics of scalar spin-off particles under Lorentz symmetry violation effects. This talk is basically for the research scholar. I am going to present. Whether my slide is visible?
Yes. Yes, sir.
Okay, so first one I will start from quantum dynamics of spin-off particles. Then we know this is the Dirac equation for gamma Dirac matrices, and this is the equation. Second one, the quantum dynamics of spin-off particle is described by the famous Klein-Gordon equation that we can express in this equation. So these two equations we will use under a different scenario. So we will introduce this nonlinear coupling of the particle with the Lorentz violating background, or we can say the Lorentz symmetry violation, in the two ways. One is for the torsion free, and another is the torsion like coupling. In 1990, the torsion free coupling was first given by this minimal substitution of this partial derivative. M is the electromagnetic for vector potential, G here is the nonlinear coupling constant, and F alpha beta is the electromagnetic for vector potential, and this V nu is the fixed for vector that acts as background which breaks the Lorentz 70. So this first proposition was given in 1990. So this coupling was specifically for the fermions, and we used to study the dynamics of the fermions using the direct equation. For the torsion like non-minimal coupling, that was another given in 2005 by minimal substitution of this partial derivative, this one. While this gamma phi is, we know this is the fixed gamma matrices, and V and this are F mu is given mentioned earlier. So this is for the torsion like nonlinear coupling. Then one can study the fermions by replacing this four vector with this one. Another nonlinear coupling that one can study is the fermion sector under the effect of Lorentz symmetry violation that is given in 2012 as a lesson 13 for this substitution. Now here one can see, so gamma nu it is known as the direct matrices F alpha beta. So this KF mu nu alpha beta, that is a new tensor field that governs the Lorentz symmetry violation. So the details of this tensor field given in the standard model extension. This is behaves as the Riemannian tensor. We will discuss it later on. But for the spin zero case, if you want to study the Lorentz violation for the spin zero particles, then this is the modification of the Klein-Gordon equation that was first given in 2015 by the physicist. This one, this is the theoretical model, where they have considered this AF here and F mu, we know that is the electromagnetic field tensor. So therefore, this kind of minimal substitution is for the spin zero particle, and the previous two for the Fermion sector or the spin half particles. Now in 2002, there is one paper that says that CVT violation implies violation of Lorentz invariance. So if the CVT invariance is violated in an integrated quantum field theory, then the theory also violates the Lorentz invariance. So these are the three possible ways, that is for spin zero as well as the spin half particles. Now we are basically interested on this spin zero particles under this Lorentz symmetry violation. So therefore this KF, here we have given this KF can be expressed in this form. This KF has the same symmetry as the other Riemann tensor in general relativity. As we know, it is a Riemann curvature tensor that has various several properties will be there. So this tensor field that we have introduced through the non-minimal coupling in the wave equation has also the same properties. In addition to that, this tensor, new tensor, has double null traces. As we know, Riemann tensor has 20 independent components. So therefore, this tensor AF mu alpha beta has 19 independent components. And these 19 independent components we can express in 4 3x3 matrices, that is kappa D, DB, HE and HB. That is given in details in these two papers. So these 3x3 matrices are defined in terms of this gap tensor by this one, where Ij runs from 1, 2, 3, that is the special part. So if we substitute this one, then in the Klein-Gordon equation, then one can find this Klein-Gordon equation in this form, in the Minkowski flat spacetime. So this one is no part, and this is the additional part that contains the Lorentz symmetry violation. While E and B as the electric and the magnetic field of the electromagnetic field tensor. So one may choose here maybe electric field or maybe magnetic field or maybe the combination of both electric and magnetic field by having the mass of the stellar particles. So we consider say one possible scenario of the Lorentz symmetry violation. This Kd constant, Kdb constant, Khb constant. These are the constants, these are independent in any coordinate. Independent field configuration that we have given here E and B, one can write in this way. This is the electric field and this is the magnetic field. electric field radial direction, magnetic field is the that direction. So in literature, several authors consider this FR is a linear electric field, keeping fixed this magnetic field constant, or maybe the magnetic field variable. So in latest work that we have done, we consider this magnetic field to be the variable, which is the linear function of this R. One may can study for 1 by R also, which we are working right now. So there is another coupling for the spin zero particles. Here this one, this beam unit is the 4 vector that acting as the background which breaks the Lorentz symmetry violation. We did a few words related to these equations published in EPL, Modern Physics Letter A also. So one may can study. Now there is another part will be there that one can study the dynamics of this spin zero particles in the presence of the potential also. Scalar potential. So this scalar potential can be introduced in the wave equation through the substitution, or m goes to m plus this one. There is another way that one can introduce the potential through the minimal substitution to wave equation by substituting this covariant partial derivative del mu equal to del mu I n. That is the fourth component of the electron vector potential. So this is another step. So one can consider this scalar potential to be static, and various types of potential will be there, like the Conrad type, linear confining potential, Coulomb type potential. One may consider also inverse square also there, which I have literature. So considering this scalar potential also, one can study the dynamics. One may can also study the dynamics of spin zero particle by considering this electromagnetic vector potential also. So here I am given one possible way to study with the potential. So this Lorentz violation has various investigation in the context of principal dynamics uncertainty principle, rainbow gravity that has been studied by many authors. This Lorentz violation has been investigated in black hole thermodynamics also and in other branches. This Lorentz violation and the CPT has been tested in the hydrogen and anti-hydrogen in this paper from mu and A spectroscopy with enormous magnetic moment, impelling phase, and mu spin precision. So therefore, we can see that these are the possible ways to study the spin half particles as well as spin zero particles under the effect of Lorentz violation. So this Lorentz violation actually comes from the standard model explanation that contains the CPT event part, CPT odd part, and the electromagnetic part also will be there. As we know, it is the extension of the standard model which includes the gravity. So the research scholar can study this dynamics of these particles and the Lorentz violation by using maybe for the spin half or maybe the spin zero particles. So these are the tests we have done in 2022, published in Professional Society A, European letter, and accepted recently in Indian Journal of Physics. So thank you so much.
Thank you, Dr. Ahmed, for taking time. Okay, it's now open for discussion. So any question? Yes, one question. Please come here.
Hello. Hi, Kajuddin. So I want
Yes.
to ask one question. So can you explain what is the Lorentz symmetry? Please explain what is Lorentz symmetry violation.
Lorentz violation. Hello?
Yes, you are asked to explain what your Lorentz symmetry violation is.
Okay. So here Lorentz symmetry violation is indicates in differently here. When the minimal coupling breaks the symmetry of this one. That is not the original Lorentz invariance, or we can say the Lorentz symmetry by the spinning top or maybe the some other. Here is the dynamics of these particles. We can study under this rule. Here consider in the base of the standard model extension that says if we introduce this non-minimal coupling, then it will automatically breaks the Lorentz symmetry.
Yes, yes, one more question, please.
He is listening.
Hello? Hello?
Yes,
Yeah, there is one more question.
yes.
Yeah, so Dr. Fajruddin, it's a very nice talk. I have a query. I am not expert in
Take
this.
it, sir, take it.
Yeah. So my query is, how will you relate your work with astrophysics?
Astrophysics. So right now, I did not study this one related to astrophysics. In near future, we will study these things. We can whether we can match this one. Here we study basically the dynamics of the particle. How the particles of the spin half or within the particle are affected by this standard model extension background, or you can say the Lorentz symmetry background, that we introduce to this minimal non-minimal coupling. Maybe either it is a vector, maybe it is a tensor field in the presence of electric and magnetic fields. The behavior of this particles in
Hello, Dr. Faizuddin. I am Sanjeev here.
Oh, hello sir.
Yeah. So what Dr. Himadri thus asked you is quite relevant question. Because in near future you can try to check whether astronomically you can make your work relevant. Because if you look into recent works of LIGO, they are trying to test these violation of Lorentz invariance through gravitational waves. Okay.
Okay.
So that may be a potential target for your theoretical frameworks.
Yes sir.
Thank you. Thank you.
Is there any more question? If there is no more question, let us thank the speaker once more. Okay, thank you, Dr. Ahmed.
Thank you sir. Thank you.
I will be talking about the properties of accretion disk in the modified gravity, and this work is collaborating with Professor Sayan Chakrabarty and Santavata Das from IIT Guwahati. So, this is the outline. I will skip this. So, but sir, let's start with what is a black hole. So, in general, we know like black hole by definition is a black, and nothing can escape from it, not even the light. So, how to detect the black hole? That's the first challenge that every astronomer is facing. So, how to do that? So these two images are actually a black hole images. M87 Sagittarius A are well-known images, and this black region is actually a black hole. So how they detect it? That's the first question. So you cannot actually detect a black hole, but what you can do is you can rely on the outside material which is accreting around the black hole. That is what we call the accretion disk. For M87, you see this right way. This region is actually coming because of the accretion disk is present here. For Sagittarius A star, it's not clear it is accretion disk, but some material is there. So we are seeing some matter evolving, and this brightness is coming from there. That's the reason we know that there is a black hole. So objective of my study is like to study the black hole in the modified gravity. So now the question is, why do you need modified gravity? So already Professor Sanjeev already mentioned this, why do you need the modified gravity? So I will just explain quickly why it is needed. So there is a limitation of the Einstein gravity coming from the cosmological scale. It cannot explain the acceleration expansion of the universe. If you want to explain it, you have to incorporate dark energy and dark matter. So if you accept the lambda CDM model, but there is another problem. How will you explain the magnitude problem? How will you explain like why this lambda cosmological constant having the very high energy if you calculate the vacuum fluctuations in the GR? Another problem is the coincidence of why the dark matter density and dark energy density is same in the current report. It's very unlikely because they both evolve very differently. Not only that, there is another problem, the missing mass problem. If you see the galaxy rotations curve, in the galaxy clusters, you see the curves, the radial direction, radial velocity of the galaxies it increases as you go away from the center of the galaxies cluster. So why that is happening? If you take the example of the solar system, your sun is the center, you go away from the center, your radial velocities will decrease, but it is not decreasing in the clusters. Why is it happening? This is another problem. The theoretical framework is also the problem. We all know that GR is not denormalizable, but these problems can be tackled by if you take higher order derivative in the theory. So actually people have shown that if you take the higher order derivatives in the action, you can actually renormalize the theory in the one loop corrections. So all these problems made people to look for the alternative of the GR. There are lots of forms, MON, brain, low gravity. So we will mainly focusing on the FR gravity for the reason of its simplicity. Now the question is which FR model you want, or what is the FR first of all. So let's just look at the action. So instead of R in the Einstein action, you have FR. Now you vary this action, you will get the equation Q, which is a higher order derivative equation, you can see. And now the challenge is to solve this equation. So there are different ways to people are using. They a priori define a function of FR, but our task is to solve this equation a priori. You should know the vacuum solution. What is the vacuum solution of this equation number 2 for FR gravity? So for that, let's consider a spherical symmetric case, very simplistic model. It's static spherical symmetric, and you have this GRR GTD component as SR and PL for time being. So now, if you solve that equation by putting like the Schwarzschild did, you will get two independent equations, equation 4 and 5. This F is basically, if you see this dF by dr. So this F is this small f, right? And you have this x which depends upon the metric component. Now this equation does not contain any extra term. You have f, x or r is the region for it. So now how do you solve this equation? So you solve it by two ways. First, either you do what Schwarzschild did. You put the constant as RT as constant, and then you put it in equation 4. You will directly get f. This is AR plus f. So let's first use this approach. If you do this, you will get the metric component like this with setting a logarithm term here. The logarithm term is, so let's see like if this model is feasible for accretion properties or not. So now we will plot the potential for our case, which our group have derived by using completely relativistic GI. So you have this potential. If you plot this potential for the metric component that you got, so let's consider the left hand side. Because of the logarithm, you have this divergence sitting there. But you don't want that because the accretion disk is not something like which will abruptly end somewhere in the space. It spreads all over the space around the black hole. So you have to avoid this divergence. So what you can do, you tune the parameter of your theory and you put this divergence away from the boundary radius. Boundary radius is basically the outer edge of the black hole. But you see, if you do that, you don't see any changes in the near to the black hole. So this green one is the Schwarzschild one. So if there is no change, then this what is the meaning of the modified gravity? Because everything is happening near the black hole. You want some change there. So this model is not feasible to study the accretion disk. So what you do now, you go for the other case. You fix your f first, then you put that in your equations and you calculate the x. So what you do? So let's say you fix your f1 plus b by r, b is some constant, and now you see if r goes to infinity, f goes to 1, you get back your gr for sure. So in that case, you get this beautiful series in the metric components. And now if you plot your potential, plot your potential. Now it is well very good. So you see like there is no divergence, and plus you see some changes in the near black hole horizon. So now once it is clear, like you can use this model. So we will go to implement our accretion model. So okay, so for our model, these are the equation, radial momentum equation, entropy generation equation, mass accretion rate, and these are the manifestation of your energy moment, conservation of energy momentum and conservation of mass. Moving on, so we are using the equation of state, which is complete relativistic equation of state. Your theta is a dimensionless temperature, and since there is a symmetry in the time and axial direction, because the space-time is spherical, symmetry and static, so you have these two conserved quantity, energy and momentum. And so how do you solve this? So basically, so once what happens, like when the fluid is entering in the black hole, it enters with a supersonic speed, and at the outside, at the very end of the accretion disk, it is subsonic. So the transition from subsonic to supersonic, it should happen somewhere, and that transition we call the critical point. So how do you calculate the critical point? At the critical point, you observe that your dV by dr is 0 by 0, and you use the L'Hopital rule to calculate this, and by convention we take the negative value of the gradient, will give the accretion solution, which is very consistent. So if you see forward, this red one is the saddle type critical point. So basically the saddle type critical point, the solution will jump from the subsonic to supersonic using this saddle type critical point. So what we found in our model, the modified gravity parameter actually have a limiting value for which you cannot get any outer type saddle type critical point. So why this outer type is very important, I will tell you in the later slide. But there is a limiting value. After that, you won't get any outer type critical saddle point for the accretion model. So this parameter actually has some limiting value in that sense. Now, this saddle, inner and outer, you have both the saddle type critical point. For them, you can actually create a parameter space between energy and angular momentum. So I will just explain this first figure. So let's say you fix your angular momentum somewhere 4.35, and you start with the lower energy. So you go away from this parameter space where you have a multiple critical point. So you will have an inner critical point. You enter in this left side of this entropy separation line. You have this solution, which is like connecting the outer edge from horizon to outer edge. And then if you enter this side, you have this, which inner critical point will connect, and you have this outer side. Again the single circuit mode. So here this solid line is basically the accretion solution, and this dotted is the wind solution. So why this? So you see that this area below this green curve, you will get this type of solution, which will connect the outer critical point to the flow will pass through the outer critical point and connect the horizon with the outer edge of the accretion disk. So in that sense, you have a possibility of shock. So Professor Santopita just last day explained why the shock is very important for the accretion. So you have the shock for this reason. That's why I was saying like outer critical point limit is there. So you cannot have shock after that particular value of that parameter. So shock is very important. So for that reason, you actually you got that limit. So now we have plotted this parameter space for different values. So now this you can see like this is the complete region for which you can expect shock is there, and this also has a value of limiting, which is which after 1.5 you have all the parameter space with the shock of limiting. Next, we actually plotted the solution topology, how this solution changes from Schwarzschild to once you incorporate the modified gravity. By fixing the one of the parameter, you have three parameters in your theory: modified gravity parameter, angular momentum, or energy. So you fix one of them and just vary the solutions. So you actually increases your chances of getting shock. Okay, so that was the first model. So next model, if you consider just by changing this r to r square, so we saw like what can happen if we just change this term, because we will anyway get back the Schwarzschild. This fr will become 1 if you go to the infinity. In that case, you get this particular metric. Now what happens in this space time? Surprisingly, you get this. If you increase your c, you will get this kind of this is your potential. So you will get this. Infinitely large increasing potential. So what does this signify? So in our accretion model, if you so this is again we have plotted the space time parameter space, but naked singularity solution will actually give you this solution. It actually does not connect to the black hole halogen. So we actually expect that there is a naked singularity solution available in the second model, where which can be tested from our model, that the flow does not actually fall into the black hole because there is a very large barrier sitting is there. So your flow basically just closes there, no doesn't fall into the black hole. And okay, so all these things, this topologies are without the shock we have done so far, but the luminosity is always very important part for the astrophysics. So what we have did, we calculated the free emission, which is the Bremsstrahlung emission, in which basically you can consider your fluid to be consist of ion and electrons, and as the electrons loses energy, it will emit the radiation, and that radiation you can calculate from this equation 22. So if you calculate your luminosity, okay, so for both the models we have calculated the luminosity. So you can see this, for first model it goes from 32 to 34. For the second model it is about 32 to 35, and so far we have seen like second model can give you higher luminosity for the solutions. And we expect like if you do shock, this will enhance your luminosity. And so this is what we have done. We have calculated firstly we have chooses the two modified model which is suitable for the accretion solutions, and then we study their solution topology, and we expect that some particular value of parameter this shock can happen or not, and we study how the solution topology will look and along with the luminosity.
Okay, thank you for your nice presentation. It's now open for discussion.
Can I see your page number 10? Where this accretion rate equation? Yeah, the last equation. The U is velocity, right? Radial velocity. And H, what is the
It's a disk.
Sorry?
Disk.
And rho is the density. Does it not look like the Bondi accretion?
It is actually Bondi.
Spherical, yeah.
It is not a spherical accretion because you have this UR sitting there, which is basically dependent on your geometry.
Okay.
It's yeah, you can derive similarly, but it's not like it's spherical accretion.
Yeah, we use this model for the formation of the supermassive black holes, this Bondi kind of accretion.
It looks like equation of continuity.
Yeah, conjunction of mass.
That is why negative sign. And my next question is this: there was a choice in your capital F, 1 plus c by r square. Is it a theoretical ansatz or it comes from some evolution equation of this scalar field?
No, this is completely theoretically ansatz.
It's an ansatz.
Yeah. So basically our motivation is to get the vacuum solution. So it is very hard to get the vacuum solution.
That's true. Can't get gas.
Non-linearity is very difficult to handle. So we actually like initially you define your f the function of f, then you calculate the metric.
Thank you. So we hear about mostly the innermost stable circular orbit in case of a black hole. So is it the part of the accretion disk itself, or is it something like different?
Okay, so what we consider usually what happens like when you are in a stable orbit, which is scope. It's basically the point where you can actually have the material in a stable orbit.
Yeah.
Once it's crossed the scope, it has to fall in the black.
Yeah.
So ISCO is it's a part of the accretion disk. Usually people say it's the inner boundary of the accretion disk.
So that means that that inner critical point that you are showing,
It is away from this.
so it is away from that.
Definitely it is away.
Okay, so in between that, I'm just asking this a general question. So in between that, in R scope and that critical point, so I mean, how those materials then go inside the black hole?
So basically what happens like once it is going very close to the black hole,
Yeah.
its speed will increase.
Yeah.
So the transition actually happens at this critical point. If you see like let's talk about this.
Yes.
We can talk about it. So the flow is starting from outer radius of the disk. So once it is going to close to the black hole, its speed should increase. I mean, it should become the supersonic. So how will it happen? It will cross a transition point, which will basically, this is a Mach number product. When they said we equal to C, when did this happen? So this transition point is we call critical point. It crosses this critical point, it becomes a supersonic. And when there is no, so once it is supersonic, what does it mean? It will cross the centrifugal barrier, and eventually it will go fall into the ground. So once it is not falling, that type of solution we call Nyquist invariant solution.
So and also I have another question. So like you have considered these modified gravity models. So the that accretion, I mean that the geometry of this accretion in GR and in those FR models. So how we can distinguish between them? How they are different from each other?
Okay, so basically that I did not emphasize more. So you see like this first plot is for the short shell case. You don't have any effect of the modified gravity, both cases. As you increase the modified gravity, depending upon this angular momentum or energy, this topology changes. So you see like this is for the small angular momentum, you don't see any changes. If you increase the angular momentum, your multiple critical point convert to the single critical point. Sometimes multiple convert changes its topology. It actually connect the instead of inner, outer will connect to the horizon, and then it will again change the topology to the center. So these changes happen because of the modified gravity.
Okay, thank you.
Is there any more question? If no question, can you throw some light into your equation of state?
Okay, so basically, so this is the equation of we are using because this temperature gradient is very different from the inner to the outer. The disk is the outer edge of the disk.
First, signify each of the terms.
Oh, okay, sorry.
Temperature, theta, then what else?
So you have this electron density, mass density. This F is basically defined by this particular. This tau is a constant. This depends upon. I haven't written it, but this also depends upon the energy. This term number density. So basically, your F depends upon this theta. This theta is basically your temperature, which is dimensionless temperature. You don't have any dimension of this temperature.
And with respect to what is the your normalizing temperature, or with respect to what you have made it dimensionless?
Oh, KT.
Scaling parameter. What is the scaling parameter for temperature?
Yeah, KT by MEC square. Okay. So from where you can get this equation. So this is basically completely relativist equation.
Okay, so if there is no more question, let us thank the speaker once more. Okay, now the next Thamao Jam. Okay, and your topic is quantum corrections to Huggin temperature of. Okay, so R and black hole surrounded by curtains. Okay, fine, curtain.